Oh,
Hello.
Alexis, you won the race today. You were first to class. Good for you.
I'm just waking up, so
You're on your number two. You're just waking up. Did you take a long nap or did you just wake up from last night?
I went to bed like 6.
Oh, what are you working on?
My hair and
It took that long, huh?
yeah,
I thought you were going to say chemistry or something.
I got done with that like at 1.
Okay.
Yeah.
All right. Oh, let me see. Deborah's there. Okay, so we got everybody. Almost. Just for a minute. Okay. So I will do this. All right. Guys, so let me make sure Deborah's on. She's kind of there's Tiara's bouncing in and out, and Deborah's on, but she's sideways for some reason. Okay, there you go. All right, hey Tiara. Uh, guys, let's I want to pull up first the assignment sheet, and then I want to look at some of those problems we were working on yesterday, the sequences and series, and then talk a little more about what we call series today. So let me share this. This thing never wants to do this for me. Okay, there we go. All right, so a couple of things. Anybody got any concerns, questions, anything before we dive right in? I'm going to drop back a little bit to yesterday and talk about these patterns that we were looking at, because we're going to look at some more of those later. Questions, anybody? So if you look at the assignment sheet, Thursday and yesterday we were just talking about sequences. I added these few things for you to try to see some of the patterns on those, and the rest of it was finding limits of sequences, and we use things like the sandwich theorem and L'Hopital's rule and so forth. So if we're looking at just a sequence, we want to know what the limit is. We just take the limit or sandwich it between two things to find the limit, and we have an answer. This last little bit here was finding those patterns. But before I do those particular ones, I wanted to kind of wipe up what we did yesterday, and look at the ones that we were looking at yesterday, and just see what you came up with. One of the ones, and I tried to figure out which ones I had done and which ones I didn't. And I remember that one of them that we didn't finish because I was basically not looking at it properly. And that's what happens sometimes with these things. You're not looking at kind of the right pattern or how you could make it work. It was x squared over 2, x cubed over 3, x to the 4th over 4, and so on. It was pretty clear that this last piece right here was easy. It was just x to the nth over n. If you let n be 1 right there, it'll be just x to the 1st over 1st, x squared over 2, x cubed over 3. We didn't quite know what to do with this one, and I was putting it inside the sequence. What we really needed to do was just say, okay, we can't get 1, we'll just add it on the outside. All right, so your first that's the whole list of the things would look like that. Okay, so we've got a 1, and then we've got the rest of this onto it. So so it would look kind of like that if we looked at the whole thing. Okay. The other one, I don't know. I'm trying to think if there was another one. Yeah, there was. I think there was one that was one. Let's see if that's on here or what we were talking about yesterday. Yeah, let's look at. I think we basically did most of those things from yesterday. Let's look at these things. Now, help me out here. Did anybody get that? And so that it worked out so that you got those as the terms of your sequence. 1, 4, 7, 10. Anybody get anything that works there? How far, what's the pattern you see here, guys? What's the pattern?
+3.
Everyone adds a +3. So for instance, another way to look at that might be that from the first one, this adds 1 3, and then this adds 2 3s, and the next one adds 3 3s. In other words, 1 plus 3 3s is 10. 1 plus 2 3s is 7. 1 plus 1 3 is 4. That kind of saying it like that and looking at it different like that might give you a hint. Because if you start at 1 and you say, well, how many 3s do I add to it? I think that would give it to you. So if you said, or if not, and if we n is 1, that doesn't quite give me. That gives me the first 4. So that gives me a hint maybe I need to adjust this a little bit. And I could say 1 plus 3 times n minus 1. I'll erase all this when I get to the other one, because now if I start at 1, that one drops out and the first term is 1. If I put in 2, it'll be 1 plus 3 will be 4. If I put in 3, that's 3 2s, it'll be 6 plus 1 is 7, and so on. So if I can't get it started quite right, I can sort of shift the n, whether it's -1 or +1, depending on how I need to do that. So that one's a little bit tricky. How about this one? Did anybody give any thought to what 2 and 6? What was my my hint yesterday was that this had something to do with that, the factorial stuff. Can anybody see what that is right there?
I couldn't get that one.
Okay, I want to show you something. Anybody else get it? You know what 2 and 6 and 24 might be? We're gonna see this one a lot. This is why I wanted to look at this one. If I said, let's look at 1 factorial, based on what I said yesterday, what would 1 factorial be equal to? I'm running off the page here. Hang on. What would 1 factorial be equal to?
1.
1, yeah. So 1 factorial would be 1. What would 2 factorial be? And remember, it starts at 2 and it counts down to 1. So what would 2 factorial be?
2.
2. 3 factorial would be 3 2 1, which would be 6. I'm sorry, guys. I'm running off the side here. It doesn't look like it on my screen, but I'm running off the side. Let me get that. Do this right here. All right. So 3 factorial is 3 times 2 times 1, which is 6. Okay. Oh, there we go. That helps fix it for me. 4 factorial would be 4 3 2 1. If you multiply that out, you get 4 times 6 is 24. And now you're starting to see those numbers. There's 1. There's 2 factorials 2. 3 factorials 6. 4 factorials 100 is 24. 5 factorial just multiplies that thing by 5. That's exactly what we've got in those denominators right there. We got 1 in the first one, 1 over 2, 1 over 6, 1 over 24, and 1 over 120. The way we write that is that we're doing 1 over n factorial. Okay, we're doing 1 over n factorial. And unless you've done a lot with factorials, you might not have recognized that. And it would be hard to see, actually, and hard to get a feeling for that. But it's but that's what it is. It's 1 over n factorial. 1 factorial is 1, so that gives me 1. 2 factorial is 2, so that gives me a half. 3 factorial is 6, so that gives me a sixth, and so on. Okay, so that's what that one is. Okay, I'm gonna erase some of this stuff so I have a little more room to scribble here. Get rid of that. I'll get rid of that and that. I think we did this one. I'm not absolutely sure, but that was kind of an easy one to see. The numerator counts down 1, 2, 3, 4. We looked at that pattern. So I think we probably need n up there, because if we start at 1, the next one will be 2, and then 3, and then 4. And I think we did look at this one yesterday. I think 2 is 1 bigger and 3 is 2 bigger. So I think we said this was n plus 1 times n plus 2. So if I let n be 1, I get 1 over 2 times 3. If I let it be 2, I get 2 over 3 times 4. If I let it be 3, I get 3 over 4 times 5, and so on. So that's what that one looks like. Okay, I saved the best one for last here. Let me get rid of all this stuff. Let's see if anybody came up with this one. And again, they're not, the patterns aren't necessarily easy to see, but once you kind of see it, you might be able to adjust it and able to write the nth term. Did anybody get anything for this one right here? Anybody get it? What they think it might be? All right, tell me what does this remind you of when you see a 2, a 4, an 8? What the next one you think is probably, what do you think the next one's going to be? Let's say what we think the next one's going to be.
16.
Okay, I think it's going to be 1/16, but I also think it's going to have a negative on it because they appear to be alternating there. Okay, so minus 1/16. So my question to you is, when you're looking for patterns and you see things like 2, 4, 6, 2, 4, what do we got there? 2, 4, 8, 16. What is that? What are those, guys? How do you generate 2, 4, and 16? What are they? Are they powers of anything?
2.
They're all powers of 2, aren't they? Everybody agree with that? I got 2 to the first, 2 squared, 2 cubed, 2 to the fourth. And you say, well, but they're in the denominator. So listen to me think here, guys, because I'm just playing with this thing. They're in at least not these two, but these are at least in the denominator. So if it was a power of 2, there's 2 to the first. This could be 2 to the 0, but it's alternating because 2 to the 0 is 1. But now this is in a denominator. So if I look at it a little differently, maybe I could see what powers of 2 I need. So if I had 2 for the first, this would be, next one would be 2 to the 0. I'm going to take care of the alternating in a minute. Let me just look at the powers here. Could you write this as 2 to a power? What's 1/2 if I write it as 2 to a power, guys?
-1.
2 to the -1? Everybody agree with that? So how about 1/4? 1 over 2 squared is 2 to the -2. Everybody agree with me? How about 1/8? What's that?
2 to the -3.
2 to the -3. Now, I know these things need to alternate, but I'm going to take care of that in a minute. I think that if I start with this, I need a power on 2 that's going to start out with a power of 1, and then go to 0, and then go to -1, then go to -2 and -3. I'm looking for something that's decreasing here. And I want it to start with 1. What I finally came up with for this was something like this. Suppose I said, suppose I let that right there be an n. If n is 1, I get 2 to the first. If n is 2, I get 2 to the 0. If n is 3, I get what, guys?
-1.
The -1. If it's 4, I get 2 to the -2. If it's 5, I get 2 to the -3. So I was kind of looking at something that would start, when I put 1 into it, it would start at 1, and 2 would go to 0. You have to play around with it. But now I'm going to make it alternate. Let's see if we can do that. Because you can do the alternation all on its own. The first one was positive. So I need something that gives me an even number. So I'm going to put in +1 there. Because if I put in 1 again, -1 squared is positive, and then that'll be +1 times 2 to the first. If I put in 2, -1 cubed will give me the negative, and it'll give me the 2 to the 0, which is 1. And so on, it'll work out. So work out the pattern without the alternations first, and then see what you can do to just make it alternate. I mean, if n plus 1, if it starts with a 1, you want to make, if it starts positive, you want to add 1 to it so you'll get an even number. If you start with an odd number, you want to add 1 to it to get an even number, and so on. So that's what I was looking at there. Now again, they're not particularly easy to see, but if you play with them, you can kind of figure out what's going on there. Okay. Any other questions on any of the homework? Did everybody get their improper integrals quiz back? Okay. Look at my comments on that carefully and make sure your notation is good. You don't just sort of jump from place to place. You're taking the limit as something goes to very specific from the left or the right or whatever. Right. Okay.
I have a question.
Yeah, Alexis.
So, like, about the improper integrals, could you see my paper?
Which problem are you talking about? I don't think.
I'm using like a different notebook. I was just trying to see if you could see.
I might be able to see it. Sometimes I dump. Let me go back and look. Hang on just a second. Let me see if I can find it. It's in my I think it's in my Google Drive. Let me see if I can find it. It might not be graded, but maybe you can show me what I've got here. Let me see if I can get back to my Google Drive here. So it would be in assignments. Assignments. Where are those? Well, I got to go further back than that. I need. Hang on. Go back. Okay, there we go. Let me see. Yeah, that's all my Math 70 assignments. Hang on. Let's go to just that and search. I'm not sure I can. Tell me what the nature of your question was, Alexis. I'm not sure I can.
I'm basically asking, like, when I scanned it, was it clear?
Yes, it was very clear.
Okay, that's what I was asking, because I was using a different notebook because
I'm running
out of paper. So
yeah,
I'm using this little notebook.
Yeah,
what it is. I'm not buying nothing else.
That's fine. It looked like I thought you were going to ask me something about the problem, but that's fine. What it looked like to me when you wrote it is that you were writing it with a very thick, dark pen, and that's more what I need than anything. I don't care if it's on line paper or I don't care if it's on a ring notebook or anything, as long as I can see it, and I can see it when you write it really bold like that. Okay, you're using something bold. Tara, yours is usually pretty bold. Yeah. What is that? Just a regular black pen?
I got it from the store.
Okay. All right.
They have a bunch of colorful pens.
Yeah. But some of them are finer tip than other ones. The thicker ones are easier to see.
And this is a little fine tip, but I write pretty hard.
Yeah. Okay. Okay. So let me see if I can get back to where I was here. So anybody else question about anything? Oh boy, where am I here? I'm in the wrong section. Let me go back to this program. Here we go. Okay. Okay. So I was just looking right then at your week 3 online assignment. So that's where we are. What I want to start talking about today, and it's going to take me a couple of days to finish this, is 11.2. I called it A because it's like the first half of this lecture. So let's open that up. I've got some new definitions to give you. I want to talk to you about something called an infinite series. That is different from an infinite sequence. A sequence is just a string of numbers that you're trying to find a pattern for, whatever. You want to find the limit of those particular numbers. A series is things that are added together. So let me give you a real simple problem just to sort of kick us off here to see what we mean by a series. If I said to you that you put something in your calculator and you came up with 0.66666 repeating, what would you tell me your calculator was trying to tell you that was?
2/3.
It's infinite, but does it get closer and closer to anything? I mean, what fraction would you put into the calculator to get this?
2/3.
1/6.
No, not 1/6.
1/3.
2/3.
Actually, 1/3 would be 0.33333. So what do you think 0.666 is? It's 2/3, isn't it? Put that in your calculator, guys. Put in 2/3 and hit enter, and you'll see that. When it changes it to a decimal form, it looks like that. Now, I want to show you something here. If I can get to a blank page here, let me just go through this. See if I can get another page here. Maybe I can show it to you up here. So suppose I said, get rid of this thing. Suppose I said this. Okay. Suppose I said, I don't know what that is. I don't know what fraction it is, but I think we do. I think if you put in 2/3, you'll see that that's what that thing is. But suppose I didn't know what it was, and then I'll do one that I really don't know. If I said, let's let x equal 0.6666 repeating, okay? That's what I'm going to let x be. What would 10x be, guys? What would 10x be if x was 0.6666, what would 10x be?
6.666.
Well, what does multiplying by 10 do? Which way does it move the decimal?
Over.
Move over which way? Right or left?
Right.
It moves it right. Yeah, so that 10x would be 6.666 and so on. Okay? Now, I'm going to put a little trick to see if I can find out what x really is. If I subtract this right here from that, 10x minus x is 9x. Okay? Now, if I subtract 0.66666 from 6.666, what's left? Because all of this stuff is in infinite here, so what's left if I subtract this top one from 6.666? It's just the 6, exactly. Now, if I solve for x, I get x equals 6/9, and that's 2/3. So basically what that says is, that's an infinite thing there, but the more 6s you get in it, in a way, the closer it's getting to 2/3. We say that something like that, in a sense, converges to 2/3, okay? There's other ways to say things, but for right now, that's what it looks like. Let's see if I can find a blank spot here to do another one for you. I'll do one we don't know, and I don't even know it. Suppose I said, let's let x equal 0.232323 ... In other words, the thing that's repeating is 2/3. And suppose I want to say, well, what fraction is that? That's actually a rational number. You could put it in your calculator and something would give you that. So we want to find out what that is. Now, remember what we did with the 0.666. We multiplied by 10, and when we moved it over, we got the same thing, 0.666, to the right of the decimal that we had in x. What do I need to do to get the repeating part of this look to x to make it look the same? Will multiplying by 10 do it for me, guys?
No.
No, because it'll be 2.323232. That's not what I want. I want the 2/3 part to repeat. So what do I need to multiply it by to get it so that it's lined up in a sense?
100.
100, exactly. So let's multiply by 100. So if I do that, it'll be 23.232323. And then, of course, that's just repeating like the other one. I'm going to pull the same trick I did a minute ago. I'm going to say 100 minus x is 99x. And 23.232323 minus 0.232323 is just going to be 23. If I solve for x, you'll get 23 over 99. If you put that in your calculator, guys, that's what's going to give you that 0.23.23.23. If you got your calculator with you, try it. But that's a little trick. If it repeated in blocks of 3, I'd multiply by 1000x, get it in line up, subtract. Okay? That's what makes a number rational. When you've got a pattern like that, a rational number, remember, is just one number over another number, right? So that's, when you have a pattern like that, you can do that. Now, suppose you had something like pi.
Oh, God.
Why do you say, oh gosh, about pi? What's true about pi what's not true about pi that's nice about this one?
It's not a rational number.
It's not a rational number. Number one, we call it irrational. Number two, if we look at the structure of it, it doesn't repeat in any kind of blocks that I can see. I wouldn't know what to multiply it by. I mean, you can't predict the next block. You can't predict the next number. So that's, in a sense, what makes it irrational, or one way to think about why it's irrational. I can't do this procedure on it because I have no defined block of things that are repeating. Same thing with E. E is an irrational number. If you look at E is a little bit deceptive though. E is 2.71881828. And a lot of people stop there and they tend to think, well, maybe it's repeating this block, but it's not. Right after that, it starts going haywire again, and you really can't tell any kind of block that it's repeating in, okay? E and pi are irrational numbers. Okay, so let's go back. I'm gonna come back to that. That's gonna show up again maybe tomorrow. But let's go back to the beginning here. But we had the point is, oh, I just erased the point I was gonna make. That one I just did, that 0.23, 0.23, 0.23. The further you go out in the decimal representation, the closer it gets to 20, whatever it was, 23 over 99. Okay, 23 over 99. Okay, so let's sort of look at why that happens. Let's go back to the beginning here. Oops. So if I look at this one right here, I'm gonna look at it a little differently. If I just took this first 0.6, the first decimal was 0.6. If I want to get the second 6 in there, I'm adding 6.06. I'm adding 0.06. So for example, if I just wanted the first two decimals, I get 0.6 plus 0.06 is 0.66. The next one I would add would be 0.006. So 0.6 plus 0.06 plus 0.006 is the first three. And I keep going like that. We call that an infinite sum, guys. And if I look at this thing clearly, if I just looked at the first piece here, 0.6, that's 3/5. Not 2/3, it's 3/5. If I look at the next two together, plus 0.06, that's 0.66. And that's not 3/5, that's closer to 2/3. If I look at the first three, I'll get 0.666, adding those first three, and that's even closer to 2/3. The point is, the more sixes I get in here, the closer it gets to what we think of as 2/3. Your calculator has to cut it off though. It cannot write an infinite number of sixes. And that's what we're looking at. We're looking at an infinite sum. So 0.66666 is the same as 6/10 plus 6/100 plus 6/1000 plus 6/10,000 and so on. And for every one of these things you add on, you're getting something a little closer to 2/3. Okay, it's just getting closer and closer to 2/3. Now, if you look carefully at this one, that's 6/10, 6/10 squared, 6/10 cubed, 6/10 to the 4th. So here's what we say about that. I can write that in the following way. If I've got all these things added together, and the more I add, the closer it's getting to 2/3. And when we say closer, we think, well, a limit. So this sum here has a limit, and it looks like that limit is 2/3. When we want to write a sum instead of just individual pieces in a sequence, we write it like this, okay? That sigma right there is read the sum of, and you may have, raise your hand if you've seen this before, whether you remember it or not. Everybody's seen it, okay? All right, good. What it means is to start at n equal 1 and plug that value in. So like right here, I plugged in 1 and I got 6/10. And then the summation means to add the next term. If I let n be 2, I'll get 6 over 10 squared. If I let n be 3, I add on 6 over 10 cubed. 4, I get 6 over 10 to the 4th, and so on. So that thing right there, these two things we say are equal, and we talk about it as an infinite series. An infinite series. Okay. Again, it's not a sequence, because a sequence is just one number, a comma, another number, a comma. These are elements of something that are all added together. Okay, so here in general is what I want to say about that. Mostly today we got terminology, but it says an infinite series is an expression of the form A1 plus A2 plus A3 plus AN. Notice when I defined a sequence, I had commas in between there. Now I've got summations. That's what that sum sign is what that's equal to. So if you let n be 1, you'll get A1. And then you add on the next one. If you let n be 2, you'll get A2. Let n be 3, you'll get A3, and so on, up to infinity. Now, if I stop it, it's not an infinite series. If I stop it at 4, I would just go to 4 and stop. But it goes to infinity if it's an infinite series. So I'm looking at then plus ... Okay. So also, each one of these things, A1, A2, A3, is called a term of the series. And the AN is called the nth term. So that nth term there is the roadmap that I use to build this sequence in, or this series in. There's my roadmap right there. Let n equal 1, plug 1 in. Now let n equal 2, plug that in, add all the things together. Okay, does everybody see what I'm doing? Let me give you one to see if you can figure that, just write this out. Suppose I said, what's the sum from n, or write out a few terms of the sum from n equal 1 to infinity of minus 1 to the nth times 1 over n squared. You guys take a minute. I want you to write the first 4 terms of this series. Right there, minus 1 to the nth times 1 over n squared. I want the first 4 terms. I'm just starting with 1, and then go to 2, and then go to 3. Okay, let's everybody looking up. I got Alexis looking up. I got Tier. Okay, I got everybody looking up now. Did you get that? Minus 1 plus 1 over 4 minus 1 over 8 plus 1 over 16. Everybody get it?
Yeah.
Okay. So that's what we call an infinite series. And it doesn't stop, guys. It keeps going on in that pattern. Okay. So we might be out, occasionally we're asked to look at that thing and find out what the series is that generates those numbers. Okay. So let's look at something else here. So what's the question really is, what do we mean by an infinite sum? We said that 0.666 could be broken down so that it looked like a sum of things, like 0.6 plus 0.06 plus 0.006 plus 0.0006. And here's this, what we call an infinite sum here. Now what we said was that it looks like this is the one that's just getting closer and closer to 2/3. And in the end, we're going to say, if that's what it's getting closer and closer to, we're going to call that the sum. Even though this is an infinite thing, it's reaching a limit. But it's not just each piece that's reaching a limit, because if you just looked at 6 over 10 to the nth, that would go to 0, okay? So we're not just looking at the individual piece here, we're looking at the sum of these things. So here's what I want to talk about. What's meant by an infinite sum, what you're meant to do is look at the sequence of partial sums. So what I mean by the sequence of partial sums is this. If I want, here's this thing right here. And if I want to know what S1 is, essentially when I'm looking at this series, and we said it was 6 over 10 to the nth power, from n equals 1 to infinity, S1 is the first one of these. Now it's the sequence with partial sums. The important thing about that thing right there is the word partial. If I let n be 1, I get 0.6. What S2 says to do is, okay, we want you to go 2 terms down in the series. So if I go 2 terms down in the series, it would be 6 over 10 to the first plus 6 over 10 squared. So that's S2. That's a partial sum. If they asked me to find S3, it would be, I go 3 into it. So I'd have 6 tenths plus 6 hundredths plus 6 thousandths. That's my S3. Notice every one of these, this is 0.6, this is 0.66, this is 0.666. If I ask you, that's a bad one, 666 in lots of ways, hang on. So 0.666. This next one is 0.6666. Now, if you look at just those numbers, that is a sequence, but it's what we call the sequence of these partial sums. So we want to know, are these sums getting closer and closer to anything? And it looks like that sequence of partial sums is getting closer and closer to 2/3. So let me go up a little bit with what I said. So the sequence of partial sums is 0.6, 0.66, 0.666, and so on. Now, I got another definition for you. The kth partial sum, and that's a weird way to say something, guys, the kth one, it's just the one that's the number k in line. But the kth partial sum of a series is this thing. Sk, you take this and you take k of them. If I said the 5th partial sum, you take 5 of them. If I said the 10th partial sum, you take 10 of them and add them together. But the kth partial sum looks like that. And the sequence of partial sums is S1. And let me show you what would be in that. S1 would just be A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3, and so on. You're just adding one every time you go. So Sk would be A1 plus A2 plus A3, all the way down to whatever K was. I don't know what it is, whatever it was, okay? So those are what we call partial sums. And those partial sums form a sequence themselves, okay? Question, anybody? This is one of the questions that's always asked on the senior math exam. Just to give you a little heads up in case you ever think you want to finish majoring in math or whatever. It talks about what does it mean for an infinite series to converge or to have a limit. And what it means is that the sequence of partial sums has a limit, okay? All right, so let me go a little further. It's easy to see that this one looks like the sequence of partial sums converges to 2/3. That's one, you know, you're like, yeah, it's getting closer and closer to the 2/3 because I know my calculator, when I put in 2/3, will give me as many 6s as it can, okay? So it's getting closer and closer to 2/3. Some of these things aren't that easy to see. Let me give you an example here. This one's kind of a mess. Well, not a mess, but it's certainly, it's more complicated than the one I was looking at before. If I say, here's the series from n equal 1 to infinity of 5 over 5n minus 2 times 5n plus 7. And I want to write out some of the terms here. I just write them out. If I let n be 1, I get 5 over 3 times 12. Just plugging in 1, I'll get 3 there and 12 there. The next one will be 5 over. If I plug in 2, I'll get 10 minus, 10, is that what I, well, oh, I'm sorry. If I plug in 1, I'll get 3. If I plug in 2, I'll get 10 minus 2. That should be a 3 there, guys. Something looks weird the way I've got it. Well, I don't really care what it is at this point. But what should it be if n is 2? 10 minus 2 should be what, guys? It should be 8, shouldn't it? Let me see if I did that on the other one. Okay, I'm gonna leave it like it is. Nah, I can't change either one of them. I'm gonna say it, suppose I have a 3 there. Okay, let's try it again. So the first one's gonna be, if n is 1, that's not gonna work either. Hang on. Have I got it wrong? If n is 1, I'll get 3 times 12. If n is 2, I'll get, certainly get 17 there. But if n is 2 right there, I'll get 10 minus 2. This should be 8 right here. Sorry, I think. If this is 3, I'll get 15 minus 2, which will be 13. And 15 plus 7 is 22. So I just made a mistake in that one right there, guys. Is that right? N equal 2. But if I keep writing, that'll be the series right there. Now, here's how I look at the sequence of partial sums. S1 is just the first one. S2, correct my mistake here. S2 is the first 2. S3 is the first 3. S4 will be the first 4. But let me show you something here, guys. I want you to take your calculators out and tell me what 5 over 36 is. And I'm gonna go to my calculator. What I want you to do while I'm finding my calculator, find a decimal form for all of these fractions right here. And that should be an 8 right there. Add those fractions and find decimal forms for them. Okay. We'll see if we all get the same stuff here. First one's easy. Okay, let's probably see if that's what you're getting, guys. Have I got agreement on the first one, guys?
Yeah.
What I think happened on the first one is that it was repeating 8s, and eventually my calculator just rounded that last one off to 9. Does that look like what you got? How about S2? You didn't get that one? Okay, let me try it again. Did anybody else get what I got? Anybody gets that? Get that? Did I screw it up? Okay. Did you change that to an 8?
Yeah.
Okay, let me try again. I tell you what, I can make this a little quicker by doing the following. I could just take that one that I had right there, 0.13, a bunch of 8s, and a 9, and add it. Since it already added that one, I'll just add this one. If you put in 5, make sure when you divide, you get parentheses around 8 times 17. Because if you don't, the order of operations is going to divide first.
17?
Yeah, 0.1756. Make sure when you put it in the calculator, the denominators get in parentheses.
See, I thought those were like decimals.
No, I'm sorry. It's 8 times 17. No, this is, see what we did up here in the function? We were multiplying. Okay?
Yeah, well, then.
So let me try the next one again. So if I want the next one, since I've already added the first 2, all I have to do is add this one onto it. So I'm going to add 5 divided by, and it is times, guys, that's 13 times 22. And I get, yeah, 0.19313611123. Deborah, are you getting those numbers?
Mm-hmm.
Okay, Tiara, you getting them? Yes? You are? Okay, you got it? Everybody got them now? Okay, so yeah, those are times. Now, here's my point. So should be getting those numbers. This isn't as easy to see where it's going, but it is going somewhere, maybe. I don't really know for sure. I get a 0.13, I get a 0.17, that's about 0.04 units apart. This time I get a 0.175 and a 0.193, that's about 0.2 apart. If I went to the next one, I might get something a little closer than that. Maybe it is reaching some value or finding some limit, but it's really hard to see, okay? So what we're gonna have to do is find a way to find the sums of these things or these partial sums and see if we can figure out what their limit is. All right, okay, let me go to one more definition here, guys. It says a series AN is convergent if its sequence of partial sums converges. In other words, if the limit of that sequence of partial sums, kind of like those funky numbers we were just getting, is approaching some value S, which we couldn't quite see, but if we could see it, we call it the limit S, the sum of the series. Like 2/3 is the sum of the series 6.66666. Okay. We write the sum is equal to the sum from A equal 1 to N. So for instance, in the one we had that looked like this, the sum from N equal 1 to infinity of 6 over 10 to the nth is 2/3. That appears to be, we need to nail that down a little more, but it appears to be what that is, that sequence of partial sums is approaching. If a series has no sum or the limit doesn't exist of the sequence of partial sums, it's called divergent. Now, I want to do one more example here and we'll call it a day. Suppose I said, what does this thing do? I'm going to write out some terms of this thing. If I let n be 1, I'll get 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, plus 1 over n times n plus 1, and so on. That's what the whole thing written out goes, and it keeps going. Okay. So the question is the sequence of partial sums getting closer and closer to anything? Well, let's do the sequence of partial sums. Let's look at S1. If I just take the first term, it's this one. It's 1 over 1 times 2, and that's a half. If I take the second one, it's the first one plus the second one, and I wind up with 2/3 there. If I take the first 3 and I add all those fractions, I get 3/4. Look at the pattern there, guys. You got 1/2 for the first one, 2/3 for the next one, 3/4. What do you think the next one's going to be?
5, 6.
I think you skipped one. How about 4/5 and then maybe 5, 6? Okay. So anyway, if you look at the pattern, it looks like that. For instance, the second one is 2 over 1 more. The third one is 3 over 1 more. So when I'm going to say, well, that means that the nth one, which if I look at the pattern, The nth one is n over 1 more. And 1 more means you're just going to add 1 to n. Now, here's something I want you to see. And you can do this as part of your homework night because you're not going to have much homework because I didn't get very far. This thing right here, I said that these two things were equal. I think you can show that by partial fractions. If I wanted to split that up into 2 fractions, it would end up looking like n over n plus 1. If you said a over n plus b over whatever. Anyway, if you found a common denominator there, that's what you would get. So in other words, another way to write this is that. Now, I'm going to write out Sn. Now I'm going to write it out. I'm going to write it out using this. It is the same. You can show it's the same as n over n plus 1, but I'm going to write it out using that. So Sn is going to be 1. The first one's going to be 1 minus 1 over 2. The next one's going to be 1/2 minus 1 over 3. The next one's going to be 1/3 minus 1 over 4, and so on. Now, when I get to the end of this thing, it's going to be 1 over n. See, it's alternating. It's going to be 1 over n minus 1 over n plus 1. Now, I want you to notice something else about this. First of all, let's go back. What do you think? What do you think? 1/2, 2/3, 3/4, 4/5, 5/6, 6/7. What do you think that's getting closer and closer to? What if I went out to 100 over 101?
1.
It looks like it's getting closer and closer to 1. I want to show you how we can see this. If you look at this thing right here, and that again, that was just S1, that's S2, that's S3, that's S3, that's S4. I want to regroup these things. Look at what happens when I look through it. What happens to minus 1/2 and 1/2? They're gone. What happens to minus 1/3 and 1/3? They're gone. Minus 1/4 and a 1/4, it's gone. The next one's a 1/5, it's gone. This one right here went with the one right before it. So the whole middle part of this thing collapses. It's called a telescoping series. In other words, you've got a telescope that's way out and it just collapses. And what we were left with is 1 minus 1 over n plus 1. Now, because that is my Sn, I'm going to take the limit as n goes to infinity of that. And the limit as n goes to infinity of that thing right there goes to 0. It is 1. That tells me that the sum of this series right here is 1. Its sequence of partial sums here is getting closer and closer to 1. And it collapsed like this, and it's called a telescoping series. There's not a lot of homework to do. Let me show you what homework I want you to do, because it's not much of what's on there. And you can look at this again, but let me show you what we've got here. Where'd it go? Here. All I want you to do for homework is finish up what you hadn't finished up for wherever you are. These things right here. Those are examples of the last thing I did. They're called telescoping series. If you write out all the SNs, things collapse in the middle and you can take a limit. And that's what you want to do. So just 1, 3, and 5. That's it. That's it. So you can work on those, get them done. Work on other things tonight. All right. We doing okay? Yep. Questions? All right. I'll see you tomorrow. Okay. Go to bed early tonight, Alexis, please. She left.